Sir, is my screen visible?
Yes, madam.
Yes, sir. Okay, so in the afternoon session, we are going to see metamaterial split ring resonator design using HFSS. So before going to see how to design the split ring resonator, first let us see the fundamentals of metamaterials. Okay, actually the metamaterials in today's communication systems, everything is in compact, like right. So we need to design a very miniaturized components, communication components. So we need to be very, I mean, the device has to be very smart. It should be in smart nature. Okay, so now the antenna construction itself has become in such a way that the component size has to be in terms of millimeters. So there are so many microstrip antenna technologies which are offering miniaturized sizes. Okay, but we have to look into the properties of the microstrip antenna so that the overall area of the antenna can be reduced, but still the operating frequencies and other properties still remain the same. So these can be achieved by means of high permittivity dielectric substrates, or using shorting walls or shorting pins, or any other like using fractal geometries, etc. So we can reduce the area of the microstrip antennas by using these different methodologies. Okay, so but these methodologies have show many disadvantages, such as narrow bandwidth and low gain. So in order to overcome this disadvantage, a new type of solution has been introduced, which consists of an electromagnetic metamaterials. Okay, so the use of metamaterials in antenna design, they not only reduces the size of the antenna, but also improve the other antenna parameters, such as bandwidth, gain. Okay, which are the disadvantage of the normal microstrip antenna design. Okay, so that's the reason we are looking for metamaterial structures in the antenna design. Okay, so I mean, what is meant by metamaterial by definition? Actually, the word metamaterial is a combination of two words, meta and material, which is derived from the Greek word meta, means which is something beyond, which is actually altered by its nature, or changed, or changed to something in advance. Okay, so and that means it is an artificial material which is uh, designed in order to obtain the physical properties that do not exist in the natural materials. Okay, so metamaterial is an artificial material which we have created, uh, where its physical properties does not exist in any of the natural materials. So such type of materials are new materials that are made up of these are actually made up of arrangement of metal structures on the surface of dielectric substrates. So by simply placing the metal structures in some regular fashion on the surface of our dielectric substrates, will create a metamaterial property. That means artificial material properties. Okay, so and based on this, we need to understand what does an electromagnetic EM metamaterial means. There are so many definitions that has been given by so many scientists. So in one of the definitions, it is given like this: in the metamaterials are nothing but the artificial materials that is created by arranging homogeneous metal structures and have unusual properties that natural materials are not, in which the properties are not available in the natural materials. Okay, and in another definition, the size of an effective homogeneous structure to form a unit cell of the metamaterials must be much smaller than the guided wavelength. That means metamaterial is a very large structure, but the unit cell of the metamaterial has in that unit cell, we have the size of that particular unit cell is very much smaller than the guided wavelength. And in another definition, it is defined as metamaterials are generated by arranging microstructures that are called atoms or cells. Okay, and these atoms can be made from electrical or non-electrical or dielectric materials. Okay, so these arrangement of the atoms can be in orderly or chaotic manner. It can be formed in an orderly fashion or in a haphazard fashion. Okay, the purpose of which is to create the desired macro characteristics for the metamaterial. That means it has to impose the electromagnetic properties such that they are not available in the natural materials. Okay, so the history of the metamaterials has dated back since 1898, which is first time our own Indian physicist Jagdish Chandra Bose has Sir Jagadish Chandra Bose has named a special type of material as metamaterial, which is nothing but a jute substrate. Okay, so by using that substrate, he is able to actually change the polarization of the electromagnetic wave. Okay, so and later after that introduction of that particular material properties, later the scientist, Russian physicist again, Victor Veselago, okay, in 1967 has first proposed the metamaterial structure. Okay, and later other scientists like Pendry and Smith, they have realized complete metamaterial based on the split ring resonators. So if you can see, you can even take the proceedings of Royal Society of London. In that, the proceedings are dated back to 1998, in which Sir Jagadish Chandra Bose has written an article based on the metamaterials. Okay, that was the first publication on metamaterials, right? And later, as I said, this is the paper the Russian physicist has written, and in that negative permeability material has been introduced. Okay, this was the first time where a electromagnetic material has been created using natural materials, but its electromagnetic properties has been changed. Okay, a negative permeability substrate has been material has been created by changing the material structure, but not the composition of the material. Okay, so that was the first time which a negative permeability structure has been introduced, and later by D.R. Smith, another physicist, in the year 2000, he has proposed a complete metamaterial structure by introducing negative permittivity material also. Okay, it is a he has introduced a split ring resonator in which it consists of a negative permittivity as well as negative permeability material. Okay, so this is actually a figure that shows a right hand medium, the electric and magnetic waves in the right hand medium, and how the electric and magnetic waves and the wave will be propagated in the left hand medium. Just a difference between the natural materials and how the waves will be propagated in the metamaterial. Okay, first one shows the natural material, which is nothing but the right handed medium, and the second one shows the metamaterial wave propagation, which is nothing but which is nothing but we call it as a left-handed medium. Okay, so in the first figure, it is if you assume that it is an isotropic and homogeneous medium, the values of epsilon and mu, which are permittivity and permeability, they are both positive, which are naturally which are in the materials that are naturally occurring in the nature. Okay, so in this medium, the electric field and the magnetic field, okay, electric field, magnetic field, and the propagation vector form the right-handed orthogonal vectors. Okay, that means that's the reason we call this as right-handed medium. And both the wave that is propagating, that is S and K, are in the both in the same direction in the right-handed medium propagation vector, and the S is nothing but the power density. Okay, that is nothing but E cross H. S is nothing but the pointing vector E cross H. They both are in the same direction, whereas in the left-handed material, if you can see, the electric and magnetic field are perpendicular to each other, but the S vector and the K vector are both in the opposite direction. That means that means this type of material will support the backward waves. Okay, that is the energy and the wavefronts. The energy, that means yes, and the wavefront, that is propagation constant, both are traveling in the opposite direction. Okay, that, and hence the name left-handed medium. Okay, so in such materials, actually epsilon and mu both are termed to be negative. Okay, so because of some abnormal physical phenomena which occurs, such as this actually will show you the left-handed material behavior. Okay, and also behavior of the reflection, refraction, and diffraction. Okay, if you can see, there are 4 coordinates. If you plot the values of mu on y-axis and epsilon on x-axis, if you can draw the graph epsilon versus mu, then in the first quadrant, both mu and epsilon are positive. They are treated to be positive, and these are the naturally available materials. So in this, the refractive index is given by positive value. What is the refractive index? Refractive index is nothing but under root of mu into epsilon. Okay, this we already know. So both are being positive, your refractive index is also positive, and hence we term this type of materials as double positive material or right-handed materials. Okay, in this, as you can see, this is the incident wave, this is the reflected wave, this is the refracted wave. Okay, this is just a indication of how the waves can be reflected and refracted. Whereas in the second coordinate, and in the fourth coordinate, if you can see, epsilon is negative here, and in the fourth coordinate, mu is negative here. That means if either one of these parameters are negative, then the refractive index becomes imaginary and there will be no transmission takes place. Okay, so when the values of mu and epsilon, either one of those values are negative, then there will be no transmission at all. Whereas if you can see in the third quadrant, where both the material properties mu and epsilon are negative, what happens to the refractive index? Refractive index becomes minus under root of mu epsilon. The refractive index is becoming negative. What does that mean? The refracted wave will be propagating in the backward direction. The wave will be propagated in the backward direction, as you can compare with the quadrant 1 wave with the quadrant 3 wave. What is the difference? You can see this is in the forward propagating mode, whereas this is in the backward propagating mode. Okay, so that is this actually forms the metamaterial properties, and this we call it as left-handed material or medium. Okay, so even in this slide, you can see how the diffraction or refraction takes place in a liquid which is having a positive refractive index, which is shown in figure A, and with the refractive index being 1, which is shown in figure B, and with the refractive index negative, which is shown in figure C. Okay, so here there is a positive refraction, and hence the needle in the liquid can be seen like this. See, yeah, whereas this is called as the positive refractive index or positive refraction, whereas when you compare with the figure C, the negative refraction can be treated as the backward propagating wave. Okay, so this this is in the backward wave. That means negative of this the vector direction is actually exactly opposite to that of the figure A. Okay, so that's the reason we are having a backward propagating wave, okay, when there is a negative refraction or negative refractive index. So having the metamaterial properties, I mean having the negative permeability and negative permittivity properties changes the actual all these laws. Okay, what are those laws? Snell's law, that means negative refractive index, as I shown you the previously, the formula of negative refractive index of left-handed materials minus of under root mu epsilon, and also Doppler effect and Wavil, and also Vavilov-Serenkov effects. All these effects or the laws, they get reversed when mu and epsilon becomes negative. Okay, so the electric field, magnetic field, and the wave vector of electromagnetic wave in LHM form the left-handed triad. That means backward waves. Okay, so this slide can, you can see the difference between the left-handed material and the right-handed material. See, this slide shows a rectangular waveguide. Okay, the medium of the rectangular waveguide is filled in three regions. Okay, there are this entire rectangular waveguide is actually divided into three regions. Okay, this is the first region, this is the second region, and this is the third region. In first and third regions, the medium that is filled is right-handed medium. That means epsilon and mu are positive here, whereas in the middle region, actually we are having the epsilon and mu being negative. What does this properties are doing actually? The what is the phase velocity and group velocity? You know both the phase and group velocities of in which are with respect to the rectangular waveguide, but this material properties are affecting the phase velocity but not the group velocity. This you have to keep in mind. Only the phase velocities will change but not the group velocities, as the phase of the wave is changing. Okay, so if you can see the phase velocity in the first and third, it is in the positive z direction. Let us say this is positive z, they are in the positive z direction, whereas in the middle section the phase velocity is reversed. Okay, so why? Because Vp is backward wave is having Vp is minus Vg. What is phase velocity? Omega by beta, right? So omega by beta, this depends upon the beta value also, the phase shift constant beta value also. Okay, so this also shows at different angles, okay, at different angles of theta, and in different portions in the same rectangular waveguide, you can see how the wave is getting refracted. Okay, so they are in this direction, whereas in the middle section it is exactly in the opposite direction. So that's the reason we call this as a left-handed medium. Okay, so you firstly the scientists have created not directly a fully metamaterial structure, but they have obtained a material with negative epsilon. Okay, negative epsilon, meaning your only permittivity is becoming negative but not permeability. Okay, so this has been created by using the metallic mesh of thin wires for obtaining the negative value of epsilon. Okay, a mesh of mesh structure of dipoles or the thin wires are created in order to have the negative negative permittivity. Okay, so yes, so these parallel metal wires actually they exhibit high pass behavior. Okay, if you can see, they exhibit high pass behavior. This behavior is seen by the incoming plane wave, and hence the impedance of the wave, you can see as the frequency is increasing, the impedance of the wave is the imaginary section is like this and the real section is like this, and the actual epsilon value of negative metamaterial, epsilon negative metamaterial is given by 1 minus omega p square by omega square. Okay, so this is omega p is nothing but the plasma frequency, and omega is nothing but the frequency of propagation of the electromagnetic wave. So this is the first metamaterial with the negative permittivity that they have realized by using a mesh of thin wires. And later they have generated a negative permeability metamaterial by creating a split ring resonators. Okay, so this kind of resonating structures, they exhibit negative permeability. So a small cell, a unit cell of split ring resonator, it is composed of two concentric metallic rings, and they are separated by a small gap D. Okay, so each ring has a narrow slot, okay, which is cut here, narrow slot, and they are spaced 180 degrees apart. These cuts are placed in this circle, this cut is placed, and this in this circle, in the inside circle, this cut is placed in exactly 180 degrees out of phase. Okay, so the gap between the inner and the outer ring acts as the capacitors. This gap D acts as a capacitor, and the while the loops, okay, the rings or the loops, they form the inductors. So thus the combination of two rings acts as a LC resonator circuit like this as shown. Okay, so the permeability of this particular structure is given by this formula 1 minus this entire formula. Okay, so this is negative metamaterial, negative permeability metamaterial, and the combination of these two, first two materials, negative permittivity and negative permeability, when you combine the meshed thin wires with the split ring resonators, then you will be getting the negative refractive index material. We call it as double negative metamaterial, or NIM, which is negative refractive index material. Okay, so the properties of the metamaterials DNG were first achieved by combining these two structures. Okay, so this is the structure that this scientist, what is his name? Pendry and Smith. Okay, they have realized this combination, this structure. Okay, combination of ENG and MNG metamaterials, right? So the negative refractive index formula is given here, and also the permittivity and permeability formulas are given in this. And these formulas are only we will be using in the design part in the HFSS. Okay, so there are two approaches actually which we will realize the metamaterials or left-handed medium materials. One is the resonant approach and another one is the transmission line approach. Okay, so as I already told you, this approach, resonant approach, is proposed by Vasilago. Okay, Russian physicist Vasilago, and this was realized by designing the split ring resonators. That split ring resonator can be a circle in form or in a, anything which is in the loop form. Okay, so SRR at resonance, the SRR is nothing but the split ring resonator. At resonance, they provide negative permeability, and the metal wire provides the negative permittivity. So metal wire is placed in the beneath the substrate. Okay, metal wire, which is shown in the violet color, is placed beneath the substrate, and on the top of the substrate the loops are created. Okay, the loops in the sense which will give you the negative permeability. This is the resonating structure, this is the metal wire. Both combining, we will be getting negative mu and negative epsilon. Okay, so such type of this is just a unit cell, and if you have to create the metamaterial as a whole, then you have to repeat this unit cell in some periodic fashion. Okay, so SRR, these are based on yeah. So these SRR materials, okay, metamaterials which are based on this SRR, they are narrowband, bulky, and lossy. So what, yeah, based on the resonant approach, they are narrowband, bulky, and lossy. Okay, so nowadays there are so many metamaterial approaches which finds the which overcomes the narrowband disadvantage. Okay, nowadays so many metamaterial structures are available in the literature which gives you the wideband and the high gain properties. Okay, so the second approach, this is the resonant approach, which uses the SRR structure and the metal wire. And the second approach is the transmission line approach. Okay, in the transmission line approach, as you can see, okay, yeah, if you can see the first figure, it is a series, it's a uh, LC network, okay, LC network. And whereas in the B figure, it is just the opposite. Okay, here we have series inductance and shunt capacitance for the right-handed material. That means a naturally occurring material, which is not a metamaterial. Whereas in the metamaterial structure, there is a series capacitance and shunt inductance is required in order to create negative mu and negative epsilon. Okay, so this has to be reversed. This is the normal structure which we usually encounter in our transmission line network mode analysis. We usually equate the entire circuit as the series inductance and shunt capacitance, whereas for the metamaterial approach, we have to reverse these two components. We have to get the properties of series capacitance and shunt inductance. Okay, so what is the beta value, propagation constant value, if for this type of transmission line? We will be the beta value is usually written as omega by omega into under root of c LC. Okay, beta is equal to omega into LC. Whereas if you change these two, okay, interchange these two, the beta value for the left-handed medium will be changed. Okay, that becomes -1 by omega under root LC. Okay, so what does this mean? What is it having the effect? If you draw the graph between omega versus beta, that means omega by beta is nothing but your phase velocity. If you are trying to plot the graph between omega versus beta, then for the right-handed material, okay, as we are increasing the beta, the angular frequency omega, you will be observing a graph which is drawn like this. Okay, it is positive. Okay, it gives a positive beta always. Always this graph for the right-handed material always gives a positive gradient graph. Okay, whereas in the left-handed material, this we call it as the dispersion diagram. Okay, when you draw the graph omega versus beta, then that graph is called as dispersion diagram. Okay, so in the left-handed material, if you can see, if you draw the graph between omega versus beta using this formula, you'll always be getting the negative gradient. See, this will be always, the graph will be always in the second quadrant. This always it will be in the first quadrant. Okay, so that is the difference between these two, right-handed, which are naturally occurring materials, and the metamaterials, which are left-handed materials. Okay, so that this is nothing but the transmission line approach, or we can say it as non-resonant LHM approach. Okay, so how to realize the right-handed and left-handed materials using transmission line approach? See, this is a first figure actually shows the right-handed material. Okay, why I am saying right-handed material means, if you can see this, it is it's just a microstrip substrate with a metal on the top and the ground at the bottom. Okay, so this can be realized as the metal top metal can be realized as the series inductance, and the capacitance that is there in between the top and the bottom, the top metal and bottom also there is a metal, so there will be obviously a capacitance that is existing between the top and bottom. This will be considered as the shunt capacitance, as it is shown here. Okay, so series inductance and shunt capacitance, which forms this structure. Series inductance and shunt capacitance, which is forming the RH medium, RH material, that means right-handed material. Whereas here, in order to create the negative permeability and the permittivity properties, you just have to change the structure, but not the substrate properties or the any, I mean, material properties. Okay, so what we have to do, how can we get the negative permeability and negative permittivity using the same structure? You just have to split this metal line, okay, on which is existing on the top, like this. Okay, and if you can split this, there is a gap between these two, all the unit cells. I can say this as a single element as a unit cell, and there is a gap between the adjacent unit cells. Okay, so that gap acts as a capacitance. But what capacitance? It's not a shunt capacitance, because we are treating the capacitance on the same line. So this is called as the series capacitance, and the inductance can be realized, that too shunt inductance. Okay, this is actually the series capacitance and the shunt inductance, right? So this combination forms the LHM material. So the shunt inductance can be realized by introducing the vias, okay, or shorting posts. So vias can be introduced in order to realize the shunt inductance. So this is inductance, and this is shunt inductance, and this is series capacitance, which forms the LHM properties. Okay, so same substrate, if you are taking FR4 substrate here, this acts as a normal I mean uh, uh, normal material with the positive epsilon and mu, whereas if you just change the structure, this will act as a material which is having epsilon and mu values negative. How can we check this? Okay, we need to check at the operating frequency how much value of epsilon and how much value of mu is giving at the particular resonant frequency. Okay, so and we need to plot the graph, and from that graph we can able to realize that okay, this material is acting as a metamaterial. Okay, so so for that, okay, this is the combination. Okay, this is a single RH and this is single LH element. If physically, like practically, we cannot I mean design a perfect LH material. Okay, that means left-handed material. So we need to combine both right-handed and left-handed materials. Okay, so such materials we call it as composite right left-handed materials. Okay, CRLM. So such type of materials and their equivalent circuits are shown here. This is having the circuit as shown, C and L in series, C and L in shunt. Okay, so CL is the series capacitance, and L is the shunt inductance, which is forming the left-handed material behavior, and LR and CR are forming the series inductance and the shunt capacitance, which are behaving like a right-handed material. Okay, and if you can see the same in the dispersion diagram also, your RH material is shown like this with a violet color graph, whereas your CRLH, it has the both the gradients. See, it is in the negative portion of omega by beta curve, and also the positive portion is there. So this and this combination is called as the composite right left hand materials. Okay, so and the formulas are also given here. The formula to calculate beta versus omega formula is also given here for CRLH materials. Okay, so these are this is how we need to realize the metamaterials. Okay, by introducing the transmission line approach like this, and as well as the resonant approach by combining the metal wires and the resonating structures like this. Okay, so there are two such approaches in order to generate the metamaterials. So these are the applications of the metamaterials. You can find number of applications. I don't want to I don't want to read this. You can have so many applications. So Now we will see the split ring resonator design. Okay, this is in this you can see this is a metal wire, as I said. Okay, the metallic rod is nothing but the metal wire, and the it is the mesh. Okay, the mesh of these metallic wires are forming the negative permittivity property. Okay, and the split ring, that's the reason your electric field is actually parallel to this thin wire. Okay, your electric field in this materials, how the field will be propagated, the electric field will be in the direction parallel to the thin wire. And the split ring resonator, okay, this acts as a split ring resonator, and this will give you the negative permeability property, right? So your magnetic field will be perpendicular to the ring structure. Okay, and also perpendicular to the electric field that is propagating parallel to the metallic wires. Okay, so this is the kind of split ring resonator that we are designing now in the HFSS. Let's open HFSS, which I have already opened. I haven't designed it. I
Madam,
Yes,
possible, could you please switch on the audio?
sir. Audio.
Audio, sorry, video.
Okay, sir. My audio is
It's clear, ma'am.
good.
It's clear,
Is
ma'am.
clear. Okay, okay. Sir, I do not have webcam
That's
on my
why,
system.
నేను రిక్వెస్ట్ చేద్దాం అనుకుంటే క్యామ్ కనపడతలేదు మేడం అందుకని.
Yes, sir. Maybe at the end I can log in using my laptop, if it is okay for you.
ఓకే మ్యామ్,
Huh?
ఓకే.
Okay, sir. Yeah. So I did not design this split ring resonator, but now I'm going to do it. Okay. Let's create the first HFSS design, insert HFSS design in the project. Okay. And then we need to choose the solution type. So, okay, this is the structure we are constructing. Okay, so two loops with the gaps 180 degrees apart for outer ring and the inner ring. Okay, so quickly draw that structure. So insert HFSS design and solution type. Can I hide this? Read floating. Yes. So HFSS solution type, I am choosing driven model. Okay. It excites. Why model means I want to excite all types of modes here. Okay. TE mode, TM mode, and TEM mode, etc. If I choose terminal, then it excites only TEM mode. Okay. So I want all the types of the modes to excite properly. That's the reason I'm choosing model. Okay. Not the terminal. Okay, and now with this, and also here I can use composite excitation. Composite excitation is okay. We will come back to this later. First we will keep the driven options in the network analysis mode only. Okay, for any, because we are designing only a single unit cell, this will be fine. If you are going for a complex structure, that means a very big structure, a very big array kind of structure, then it is better to drive your solution type using composite excitation. Okay, so for now I'm keeping like this and press OK. And we need to set our modular. Usually modular units will be in the I'm going step by step. Okay, so first step is to insert HFSS design, then the next one is the fixing the solution type, and then third one is the setting up of the units, and the fourth one is we need to model the split ring resonator. So for that we need to draw the substrate. Okay, so for the substrate I'm taking a rectangular box. Draw the rectangular box, and the thickness of the substrate I'm giving it as 0.125 mm, and the box length is around 2.5 by 2.5. Okay, so but I am drawing in not Z but Y plane. Okay, so let us see how I am drawing. So it is my I'm giving the 2.5 by 2.5, right? So I'm starting from minus 1.25. Minus 1.25, the thickness is 0.125 minus 0.125, and the z size is minus 1.25. Okay. And the x size will be 2.5 mm and y size will be the thickness. This is my thickness, okay, 0.25 mm, and z size can be 2.5 mm. So I have created the structure like this. So I am treating like this, okay, treating the unit cell like this. Okay, my substrate is created, but we need to assign the material. I am assigning the material as FR4. Okay, FR4 substrate. So go to edit and take FR4 substrate 4.4. Okay, and let the transparency be 0.8 or 0.9, and then we need to create the rings now on the top of the substrate. Okay, let us name this box as substrate. Okay. Now we need to draw the ring. Okay, a ring on the top of the patch. Okay, so that ring I want to take not as the sheet now, but as a box again. Okay, the box which is having very, very minute thickness. Okay, so let me take again the box. Okay, again I'm drawing the box, and whose dimensions of that box are minus 1.1, minus 1.1, 0.125, and again minus 1.1, and x size can be 2.2, y size can be 0.017, which is very, very thin. Okay, z size can be 2.2. So apply. Okay, so now you have created a outer ring box. Okay, now we need to subtract this ring. Where is it? This much I need. Okay, for this ring I need to create this again another box and make the subtraction. Okay, so now I'm creating another box. Okay, I'll rename this box as outer ring. Let us say outer ring. And then now this is actually copper. Okay, we can directly give the name as copper, material as copper. Okay, or PEC, whatever. I'm giving it as copper. Apply. Okay, now I need to create another box. Okay, another box, and whose dimensions of this box are minus 0.9, that means 0.2 mm gap. Okay, that was 1.1, this is 0.9, that means 0.2 gap. Okay, so 0.125, and this is minus 0.9. So the length is around 1.8. X size length is 1.8. This is very, very thin, which is 0.017, and Z size is also 1.8. So another box has been created like this. Okay, this we need not bother about the material because we are just subtracting it. Okay, so select this outer ring and the inner ring, inner box, and do the subtraction. Now go to edit, boolean, subtract, outer ring minus inner rectangle, which is box 1. So okay, press okay. The outer ring has been created. Now we need to create the slot here, right? So this slot we need to create. So for that slot I have to draw again a okay, not the sheet, but not the sheet, but the box. Okay, what is this? I think sheet has been created. I'm canceling it and doing it. Okay, take the box and then again draw the box. Now give the dimensions to the box as 0.9 comma 0.125 comma minus 0.15. You will understand why I'm doing it. Okay, 0.9, 0.125 minus 0.15. X size is 0.2. Y size is the same thing, 0.017 thickness, and Z size is 0.3. So apply. Now see here, we have created that cutout rectangle. Okay, I mean small box. So this we need to subtract from what? From this outer ring. Okay, so select outer ring and select this and then make the subtraction, Boolean subtract. Okay, then yes, blank parts minus tool parts, you will be getting a ring like this. Okay, now outer ring has been created. Now we need to draw the inner ring. Okay, inner ring dimensions. Now I am going to draw another box so that with a gap of let's see. Okay, with a gap, I will tell you in a while. This is the box that I have created with the dimensions minus 0.75, 0.125, and again minus 0.75. So the length will be now, X size length will be 0.75 into 2, which is 1.5. And this will be the same 0.017. And the Z size will be 1.5. So apply. Now your inner rectangle has been created, which we are giving the name as, this is the material. We need to assign the material again here. This we will rename it as inner ring. Inner ring. And the material we are treating it as copper. Okay, apply. Okay. Now inner ring. Now draw another rectangle inside so that we can subtract it from this inner ring. Okay, so again draw the box and give the values in this box as minus 0.55, comma 0.125, okay, comma minus 0.55. And the X size will be 0.5 1.1. Y size is same 0.017, and this is same 1.1. So apply. Okay, you will be getting another rectangle inside this inner ring. Okay, so inner ring and this box we need to subtract. So edit Boolean subtract, and yes, you'll be getting like this. Now we need to create a cutout here. Okay, so cutout at exactly 180 degrees out of the outer ring cutout. Okay, so again we need to draw a box. Okay, now the dimensions of this box are very small, which is minus 0.75, and this being 0.125 width, and this is minus 0.15. And the length is 1.2 and the width is 0.017, and Z size will be 0.3. So please see the rectangle here. We have created the rectangle here. Okay, and we are subtracting it from the inner ring. Okay, inner ring, and this we are subtracting. So do Boolean operation, subtract inner ring minus box. So that will create a cutout here in the inner ring. Right. Now, I mean, resonator structure we have drawn. Okay, so we have assigned the properties also. We have assigned the copper properties to this resonator ring. Now we need to draw this line, which is the metal. Okay, this line. So metal line, we need to draw that too on the bottom of the substrate. So that means we need to take again a box. Okay. Again, take a box. Give the dimensions as minus 1.25, comma minus 0.125, comma 0.07. X size can be 2.5, Y size can be 0.017, the thickness, and the Z size can be 0.14. Okay, so apply. So now it is not okay because we have rotated in some arbitrary orientation. It is looking like this, but it is exactly at the center only. I have calculated the dimensions properly only. Okay, this is not wrong. So this is exactly at the center, and the two at the bottom of the substrate. Okay, so now I am renaming this as, no, this is actually the metal. So assign the material as copper. Assign the material as copper, and maybe a different color. Box 5, I will rename this as trace. Okay, metal trace. And let's give some other color. Okay, and apply. Okay, and that's it. Okay. Yes, we have created the now SR unit cell of the SRR. Okay, now we need to create the boundaries. Okay, we have created radiation boundary. Radiation boundary. It's not only the radiation boundary, as we have discussed in the morning session. Master slave boundary we have created, right? We have used, right? In the same way, because this is a unit cell and we need to have n number of cells like that. So we need to use again master slave boundary. Okay, so for that, I'm creating a air box again. I, I don't know if you know this option. There is a in this is a new version. So there is an option called create open region. You can actually create the open region with respect to your solution frequency. Here, actually, our solution frequencies are treating it as 10 gigahertz. Okay, so at 10 gigahertz, you can create the box like this. Okay, but I'm not doing it as such. I'm drawing my own box with my own dimensions. Okay, so I'm drawing the box whose dimensions are like this: minus 1.25, minus 1.25, minus 3.75, right? And X size can be 2.5, Y size can be 2.5, the original size of the split ring, okay, is the substrate. And Z size can be somewhat bigger, okay, which is 7.5. So now my box has been created like this. And this box is the air box. So I'm renaming it as air box. Air box. And the material is vacuum itself, because yes, because it is treated as the air box. And now transparency we will give somewhat like this. We can, everything is visible inside. Okay, and now we need to create the boundaries. Okay, since this is we are treating this cell as a periodic structure, right? So we need to assign the master slave boundary. Okay, and see here, I am treating the top side and the bottom side as master slave. Okay, and this side, this larger side, and that the side backwards to that larger side as master slave, and this shorter side, front side and back side, this side, I'm treating them as the excitations. Okay, right. So now let me first select the faces in order to assign the boundaries individually. So select faces and then start with the top. Okay, so top I am giving the master boundary. So assign boundary master, and we need to draw the vector. Draw the vector starting from here to here. Okay. Is it not created? Okay, that's I'll yeah. Let me draw once again. Choose this face and draw, assign excitation. Second set excuse me, I'll be back. Second set ఫస్ట్ సెట్ చేశాను, నాకు తెలియదు సెకండ్ సెట్ చేయాలని, నేను మర్చిపోయాను ఆమె చెప్పింది, నేను మర్చిపోయాను. ఆమె అడుగుతుంది నాకు పొద్దు నుంచి సెషన్లోనే ఉన్నా, 2 సెషన్. నేను నీకు పంపిస్తే మీరు చేసి పెడతారా సెకండ్ సెట్? వాళ్ళతో ఏం సంబంధం లేదు, అసలు వాళ్ళకి ఇబ్బంది కూడా ఇవ్వలేదు. Okay, so now we have to give the boundary as master and draw the vector from here to here. So now I think it is okay. Yes, and now choose the bottom face. We need to rotate this a bit and choose the bottom face, and again give the boundary as slave. Okay, slave, and that too for master one, a vector has been should be drawn from here to here, right? Okay, next. So there is 0 degree. Okay. 0 degrees phase shift. Okay, so akkada ichchanu, ikkada iddam. Okay, so I'm canceling it. Let us give the boundary from here. Okay, so that both will be pointing in the same direction. So slave master one and the new vector give from here to here. Yes. Okay, so u vectors and v vectors both will be in the same direction. Now next, and then finish. This has been created. Now this face and the backside face also is created as master slave. Okay, so select this face. Okay, the backside face has been selected now. Okay, apply, assign boundary, master, master 2, your vector, new vector, and how I should be giving this we have given the direction like this. So top direction, so let me give the direction like this. Okay, okay, we will undo it again. I'll give from this end. Okay, from this end. So again, assign boundary, master. Let me give the direction of the vector from this side. Okay, now again select the front face. The front face, that means let me rotate this master to that side. So this face, no, this face is not selected. This face is selected. Now assign boundary slave from master 2 vector. I'm drawing from here to here. That's it. Okay, this has been created. So if you can see now, there are two plates. We have created master slave boundary. One first plate is this top and bottom. Second plate is the side plates. Okay, now we are left with the other two faces. What are those two faces? Front face and the back face of the sea. I will rotate it normally again so that y will be pointing to the top. Okay, yeah, this is our structure. Okay, so this face is left and this face is left. Now for these faces, I am assigning not boundary but excitation. Okay, we have to excite this split ring resonator. Okay, so how am I assigning exciting? By using the Floquet port. Okay, by using the Floquet port. So first turn this like this. Okay, uh, yes, this face, select that face. Now assign excitation Floquet port. Floquet port will be highlighted if and only if you have assigned boundaries as master slave. Otherwise, in the excitations, Floquet port will not be highlighted at all. Okay, so once there is a master slave boundary only, you can be able to assign the excitation as Floquet port. Okay, so assign excitation Floquet port I am giving. So here also we need to draw the direction of the electric and the magnetic fields. Okay, so A vector I am drawing. A vector I am drawing from here to here. Okay, and B vector in the perpendicular direction. That means from here to here, right? So that is defined. See, this vector is parallel to the glittering resonator, and this vector is perpendicular to the entire structure. Okay, so next, and now here, if you press next, there are these two options. Here you have to be very careful in order to assign the modes. Okay, what type of modes? So in the there are two number of modes as two. We have selected the number of modes as two by default. And in the mode calculator, we have to give the solution frequency. What is our solution frequency? 10 gigahertz. Okay, and press OK. And here, this will be same as it is. And press next. Press next. Here you will be getting a de-embed settings. Okay, what is de-embed settings? We need to give the de-embedding distance. That means the distance from the Floquet port to the wall of the material. Okay, so that means our split ring resonator is here. What is the distance between the Floquet port till this point? It is actually because I have only created this box, so I know this is 2.5 mm. I'm giving the distance as 2.5 mm. Okay, so press next. This both will be applied and then finish. Okay, if you see the excitation, see here. If you see the excitation from Floquet port to till this point. Okay, so in the same way, we need to create another port. Port 1, this one is port 1, and this one should be port 2, Floquet port, again Floquet port. So again, select the face. Yeah, select the face and assign excitation Floquet port. Again, here we need not give the vector directions, because one port is already defined. It will automatically come. Okay, the second port directions will automatically come, but we need to define the modes, and we need to give the frequency for this port also, 10 gigahertz, and press next and give the de-embed system distance. What is here? This is exactly at the center. So if this is 2.5 mm, this also will be 2.5 mm. So 2.5 mm I am giving, and press next. So we have finished assigning the excitation also. Okay, so if you can see exactly like this, our split ring resonator is like this, and this is like this. Okay, Floquet port 1 and Floquet port 2. Now we have assigned boundaries. We have created the resonator structure unit cell. We have created assigned the excitations also. Now the next step, if anyone can remember, it is setting up of the solution. Okay, analysis setup. In the analysis setup, again, we have to be careful while giving the analysis setup. So add solution setup. Here you have to give the maximum passes as 25, 20 or 25. Your solution frequency is 10. And go to options. Here again, I am you. Here there is one option. Okay, this is this is what I want to tell you a new thing here. Okay, the error, the maximum delta S, which is nothing but 0.02 is there, no? Here we can set this convergence error as, uh, uh, I mean, as in terms of magnitude as well as phase. If you are not using this, it will treat only the magnitude. This is nothing but the magnitude. Delta S value is just the magnitude of 0.02. But if you choose this, use matrix convergence as like this, if you use this option, then delta S value is not only magnitude but also phase. Okay, so we are setting this as magnitude and phase. I'll tell you why we are doing all these things. You will eventually understand. Okay, so first go, even without this also we can do, but just to let you know the different options and how to use the solution setup in all aspects. Whatever I know, I'm telling you. Okay, so entry, go to entry selection here, select entries. Selected entries. In this, you will be getting two entries because you have two ports. Okay, so locate port 1 and locate port, this is first entry, this is second entry. Okay, so what do you mean by locate port 1:1 means this is one, locate port 1 means port 1, locate port 1:1. This second one means first mode. Okay, so locate port first mode. Okay, first port first mode. Whereas and we are giving the magnitude as 0.02 and the phase angle as 5 degrees. Okay, and for the entry, this also for the entry 2, we are giving the same thing. No, actually, locate port 1 second mode. We are giving second mode. Okay, so locate matrix entry. Okay, we are giving both 1:2 and 1:2. That means locate port 1 and mode 2, and entry 2 also locate port 1 mode 2. Okay, so if you select these two options and then set the magnitude as 0.02 and angle as 5 degrees, phase angle as 5 degrees, then insert. You'll be getting locate port 1. Small doubt. Let me see. 1:2, 1:2. Delta magnitude is 0.01. Okay, okay, okay. 0.01 or 1 degree, anything is fine. We can set any value. Not a problem. But this is 1:2 and 2:2. Okay. Another, we are entering another value 1:2 and this is 2:2. Okay, locate port 2 and mode 2. Here I am giving magnitude as 0.02 and this also, let us say. Okay, then press OK. So we have given the delta S value as not just the magnitude, we have considered the magnitude as well as phase. Okay, okay. Here instead of 0.02, you can give 0.01 also. Okay. Next thing is we need to options. Yes, use the basis function as second order. Yeah, in the morning I forgot to tell why I have chosen second order for array analysis or a periodic structure like split ring resonator. Even metamaterial is also a periodic structure, right? Like we designed the array, or frequency selective structures, they are also periodic structures. So for all such structures, it is better to give higher orders, because this is nothing but operating on the meshes. This option is for meshes, right? So when the tetrahedral are formed, okay, when the mesh is created, when the tetrahedrals are formed, the E and H values are solved by considering the tetrahedral face, corner, and also the diagonals. So there are three orders here: zero order, first order, second order, and mixed order, right? So zero order, we are not going to use it because it will not have much effect. It is almost negligible, so we will not use it at all. First order means it will consider the tetrahedral corner as well as the corner as well as the face. In the second order, it will consider the tetrahedral corner, face as well as diagonals in order to calculate the Maxwell's equations, E and H fields of each tetrahedral. Okay, so when you keep mixed order, it will take automatically actually it will take automatically the either the first order or the second order, depending upon the intensities of the electric field that it is observing on the tetrahedral. Okay, I don't know if you are getting it or not. Mixed first order means the tetrahedral corner and faces are considered in order to calculate the fields. When you are selecting the second order, it considers all the things: face, corners, as well as diagonals of the tetrahedrals. When you are selecting mixed order, when the intensity is more, it will go for second order. When the intensity of the electric field in that particular tetrahedral is less, then it will choose first order. If all these things, why we are doing it is to get the accurate as well as time consumption it should be minimum. Okay, so for all these things only we are exploring all the options, all the computational options that are available in the HFSS. Okay, so you can use direct solver, iterative solver, and domain decomposition, anything. Because I'm using only single cell, that's the reason I'm using direct solver. If you have to use domain decomposition, we can use domain decomposition only if, I told you in the morning, this has to be used when we are repeating the structure, and maintaining the properties of the structure as it is for the multiple elements. When we are duplicating, okay, then whatever the mesh that is being created for that initial unit cell will be copied as it is for the n number of elements that we are using. So in that way, it will reduce the computational time. It need not again create meshes, individual meshes for each and every element of the array or any periodic structure. So that particular mesh structure will be saved for the unit cell. That alone will be used for all the cells. For that reason, we will be using the domain decomposition, but right now I am not using it. Okay, so I'm using the solver only, this only, and anything else, nothing else. Okay, so I'm pressing OK. Now I have created the solution setup, right? So now we need to give the solution frequency sweep, right? So the frequency, I'm keeping that from 1 gigahertz to 10 gigahertz. And the solution frequency is 10 gigahertz, which is already given. And I'm keeping this as interpolating. I should not give as fast. Otherwise, if I give fast with master slave boundary, it will give you error. Okay, so I should be giving only discrete or interpolating. So I'm giving interpolating as of now. And yeah, I'm giving less number of points. I don't know if this works or not, but I'm telling you the procedure to design. Okay, so this interpolating, you keep it as it is and then press OK. Okay, maybe be even less, 0.5, let us say 0.5. Oh, 0.5 and the 0.25. It is giving 77 points. Okay, okay. Yes. Now frequency setup is also frequency sweep settings are also given. And what else is there? We just have to analyze, I guess. Analyze, yes, everything is properly checked. Okay, and now we can analyze, which will not be happening. We will save this project. We will see SRR. Okay, example. Right, save it. Let's see whether if it gets analyzed or not. Okay, please try this on your own. You will be getting it. Okay. Okay. Maybe I think the simulations will be stopped. Right. So machine is running. Okay. Simulation is running. We will see how long it takes. Next step is to plot the results. Here, we are not plotting the regular S parameters or the radiation plots. Okay. We are trying to see the refractive index, permittivity, permeability equations. The equations that I have shown you before here, these equations, right? Yes, these equations. We need to plot them. There are so many equations in order to get this final equations. Okay. So we will be seeing so many equations for each with respect to each port. There are two ports. So everything will be getting in two equations. So these are the equations that I have taken. Okay, from these are the equations which you can directly get from the standard textbooks on metamaterials. Okay, so this is effective impedance of at port 1, at port 2, and real part of the impedance. Okay, and imaginary part of the impedance. Next, refractive index, effective refractive index for port 2, and real part of refractive index for mode 1, mode 2, imaginary part, and then yeah, epsilon r value, epsilon r effective permittivity value for mode 1, mode 2, and what else? And also mu r value for mode 1 and mode 2. Okay, those values I have not taken. Okay, I will show you one or two equations and will try to plot the graph if we can able to complete this simulation. Otherwise I will show you how to write these equations and try to get the plots directly. Okay, let's see. That's very nice. This has been completed. Simulation has been completed. So now we need to plot the results, right? So let me take only one equation. Okay, I'll show you by literally typing one or two equations and we will check the results and close the session. Okay, so how to, there is a option other than the parameters that we are measuring usually using by creating the reports using model solution data report and using far field reports. There are so many parameters that we can measure, right? So other than that, we have an option in HFSS by creating the equation. So just right click on results. You can able to see an option called output variables. Okay, so you can plot the graph between two parameters. Okay, x and y axis, between two parameters that you can that already you know the relation between those two. I need to draw the dispersion diagram if it is in the transmission line approach, or I need to draw the refractive index diagram, or epsilon r diagram and mu r diagram. Okay, mu r versus frequency, epsilon r versus frequency, or refractive index versus frequency. All these three graphs should be drawn if you are treating the SRR with resonant approach. If you are treating the SRR with the transmission line approach, it is only good to use only one plot, which is nothing but the dispersion diagram, which is nothing but omega versus beta. Okay, now I'm showing you the resonant approach because we have constructed this type of structure. Okay, the resonator and the wire. This is nothing but resonant approach only. So I'm using the output variables in order to write the equation. So what is that equation? I'm just plotting impedance. Okay, let's plot the impedance first equation. It's a very big equation. No? Okay, well, uh, let's plot epsilon r value. Z effective. For this, we need N effective refractive index mode 1 and Z effective mode 1. So this is refractive index mode 1. And also Z effective mode 1. Where is Z effective? This one. So there are three equations I need to enter in order to calculate epsilon r effective value. Okay. So there are this epsilon r effective mode 1 expression is depending upon refractive index mode 1 and impedance, effective impedance of mode 1. Okay, so I have to enter all these formulas. So I'm trying to enter the expression name as ER underscore effective. ER somewhere here. I'll copy that from here. ER effective underscore mode 1 is equal to refractive index, effective refractive index underscore mod underscore 1. This is with respect to first port divided by Z effective underscore mod 1. Oh, this is the name. We have to just give the name here and the expression should be written down. Okay, so name is this, expression you have to enter here. So expression for that particular formula ER effective mode 1 is N effective mode 1 divided by Z effective underscore 1. Why is it showing the red in color? Red in color means error. So N effective mode 1 is not recognized in the current context. Okay, so that means we need to define Z effective mode 1 and N effective mode 1. Okay, we need to create Z effective mode 1 and N effective mode 1 first before creating this expression. So that's the reason it is not allowing. Okay, so first let me create that N effective mode 1. Where is N effective mode 1? Yes, real part and everything have to be entered now. All these formulas have to be there because see here, see here. In order to get N effective mode 1, see this is N refractive index mode 1. For that we need to define real part of refractive index and imaginary part of refractive index. What is real part and imaginary part of refractive index? These ones. Real part of refractive index is this formula and imaginary part of refractive index is this formula. And for this we need to define this and this. What are these again? These formulas. So once we know these are the actual system variables. Like system variables means the variables that we can use. Okay, these are the S parameters of the Floquet ports 1 and 2, which are already there, which are recognized by the machine. These are the variables that we have created. So that's the reason it is not recognizing. So if once your formula is in this form, then it can recognize and then it can calculate the value and then it can substitute here and calculate these values respectively, and we can finally get the epsilon r effective value. So all these formulas have to be entered one after the other. So uh, uh, I don't know, it may take a lot of time in order to enter. I will try my best. So first I'm entering this formula. Okay, I'm not calculating Z effective. I'm trying to calculate this. So N effective 1 is equal to, renaming this as N effective underscore 1 is equal to, the expression is 1 divided by, oh, effective 1 is equal to, ikkada expression 1 divided by, open braces, 2 into pi into 2 into pi into frequency divided by C naught, frequency divided by C naught
అవును.
into
ఇప్పుడు మళ్ళీ రేపు నేను అరౌండ్ 10:30 ఆ టైంకల్లా వచ్చాను.
into, it's such a big formula, a cos 1 divided by 2 into, look at port 1:1, look at port 2:1. So 1:1, 2:1 is here. Insert into expression. Okay, 2 into, and this multiplied by, again open brace, 1 minus, flocapet 1:1, 1:1. So this must be the one. Okay, insert into the expression. Then, then this whole square. So cap 2 plus, again 1:1, 2:1. So 2:1. This one insert into the expression. This also whole power 2. And another brace. And now it is showing 1 divided by, okay, 2 pi frequency of C naught. This one. So 1 into 1 divided by 2 pi frequency divided by C naught into 0.025 into a cos 1 divided by 2 into S parameters of 1:1 and 2:1 multiplied by 1 minus 1:1 and 1:1 whole square plus parameters of 1:1 and 2:1 whole square. The formula is correct. Why it is not showing? It is showing that is not recognized in the while passing expression. Missing right parenthesis for function a cos. Oh. A cos of అంటే something ఎక్కడో, yes, okay, okay, I guess we have to insert another brace here. That's the reason. Let me check this formula here. No, it has not given 1 minus whole square. Okay, anyway, this is the expression. Now we can add this. So this is added, like that. Okay, now this is added. The next expression has to be added. Okay, the next expression is, in order to calculate the epsilon r value, we need N effective mode 1, Z effective mode 1. N effective mode 1 is having this expression. So now we need to enter this. For this, we need to enter this, the real part of N effective mode 1. Part of effective mode 1 is this. Okay. Yeah. So now I'm trying to insert this equation. So now again, I am, what is this real part? Real part of ineffective. So another expression I'm adding, re underscore n underscore re underscore expression previously. Now we need to add new one, which is real part of effective refractive index of mode 1. Okay, this is the name, and the expression is for this we need to, we are depending on an effective one and imaginary part of an effective one. Okay, is there any, nothing? Okay, we can directly write the expression. So if imaginary part of n underscore effective underscore 1 is less than 0, comma, real part of n effective underscore 1, comma, minus real part of n underscore effective underscore 1. So let's check this equation. Real part of this is equal to, if imaginary part of an effective one less than 0, real part of an effective one, comma, minus real part of effective one. So add. We have added another expression also. Now what else is required? Real part is known. In the next formula, we need n effective mod 1. N effective mod 1 to LV. Effective mod 1. Real and imaginary. Imaginary value also we have to give. Imaginary, this one. So after giving the real part, now we need to give the imaginary part. Okay. It is 3:40. Sir has asked me to leave 15 minutes before. I'll try to complete within 5 to 10 minutes max. Okay. Imaginary part of this formula. This formula we have to write. So the expression is imaginary underscore n underscore. I just want to show you the graph that is being plotted using the formulas. Okay. Until and unless I define all these things, I cannot plot the graph. Since we have simulated and we got the simulation results, it is best to show the graphs. Okay. That's my intention. Effective underscore mod 1 is equal to, what is equal to, this is the expression name, and this is equal to if imaginary part of effective refractive index less than 1 of 1 less than 0, if that is the case, then minus imaginary n underscore effective underscore 1, close the brace, comma, imaginary n effective underscore 1, right? Yes. Let me check the formula once again here. Imaginary part of this is equal to, if I am n effective 1 less than 0 minus I am n effective minus 1 comma I am n effective 1. Yes, that is correct. So we have added another equation also. Now what else is it is depending? Now real part and imaginary part are added. Now we need n effective refractive index for mod 1. Okay, so that means this expression, right? So this expression we need to enter now. N underscore effective underscore mod underscore 1 is equal to real part of effective underscore mod 1 plus 1 match I into imaginary part of n imaginary part of n underscore effective underscore 1. Mod 1 is real part mod 1 plus imaginary part of effective dielectric constant mod 1. Mod 1. Okay. So two places. No? Not two places. Places. Imaginary. Let us check the formula. What I have written, n mod 1 is equal to real part mod 1 plus imaginary part of effective index mod 1. This also is correct. So I am adding this expression also. The last equation we need to write now. Last equation is n effective mod 1 z effective mod 1. Okay, so effective mod 1. Again, it is depending on series of equations. Okay, if you can, this is never ending. If I keep writing like this, it may not end, and I may be taking more time. Please understand that we need to enter all these necessary equations in order to see effective refractive index and effective dielectric constant, and I mean epsilon, and effective mu permeability. And when we, because we have simulated for the frequencies 1 to 20 gigahertz at around 10 gigahertz, when we plot the graph of effective refractive index from port 1 due to port 1, this graph, if this variable graph, which means this one, okay, this graph if you try to plot, or this graph if you try to plot at 10 gigahertz, your epsilon r value will go to negative. Okay, epsilon r will show the value negative at 10 gigahertz. This has to happen if you enter all the variables. And how to check the variables here, how to plot the variables, since this all these are done. Okay, done. You have to go to results, plot rectangular plot. Here we need to select output variables. Okay, select not S parameters, Y parameters, Z parameters, not those variables, but output variables. So whatever variables we have defined previously will come here. And we should not use DB or anything else. We have to use this imaginary and also press control and select real. So it will give you the real as well as imaginary values of whatever variable you are selecting. So in such way, if you try to plot, generate new report, you will be able to get the graph. Okay, but I don't think the graph is correct because we did not even entered all the equations. So such graph you will be able to see. At 10 gigahertz, this value will go to negative. Okay, what value we are plotting? We are plotting actually effective refractive index. Like that, you have to plot the variable effective epsilon r value. Okay, effective epsilon r value we have to plot. Then at 10 gigahertz, your value will be observed to be negative. That means your splittering resonator is showing the metamaterial properties. That is what I wanted to show you. Okay, so this is how we can design a splittering resonator, metamaterial based splittering resonator. Once the splittering unit cell has been designed and analyzed for the required frequency, again you have to create, you can use this option create array and create n number of elements. See, you can create n number of elements, make it visible, so you can able to see so many unit cells. Okay, so many periodic structures like this. Okay, so even you can delete whatever, I mean, in whatever configuration you want, you can actually delete and create your own configurations. Now it is working. See, padding option. Okay, see, yes. So like that, we can able to create the lattice structure, and again simulate for the larger structures. Okay, but while simulating such larger structures, you have to keep in mind that in the analysis setup, you have to use use HPC analysis. Okay, I mean, give the distribute your machine job over several cores that are available on your system. Okay, so that it will reduce the computational time. And then again plot those graphs for the entire lattice structure, so that you will be getting the overall results for the metamaterial splittering resonator. In the same way, you can apply this structure onto any antenna structure to create FSS structures. It's the same procedure that we follow even to while designing the frequency selective structures or arrays or whatever periodic structures you are using. Okay, I hope you how many members, I don't know. Yeah, 38 participants are there. I hope you enjoyed the session. Sir, I want to conclude my lecture.
Thank you, madam.
If there are any queries, you can ask, or otherwise you can approach me later also, well, if you are working on such projects. Thank you.
Thank you very much, madam. Participants, if you have any questions, you can place before the resource person.
Within 2 hours, sir, we cannot design the entire structure because this is a very big concept.
Yes, madam. There are 2 questions placed in the chat box, madam. You can refer to that. Or shall I read it?
So yes, we can. So there are so many textbooks are available. I'll try to design equations. Yes, all these equations are available in the standard textbooks, ma'am. I'll try to send. Okay, post me. Write a mail to me. I'll try to find the book and send it to you in whatever. way it is possible to me, I'll send the book to you. Okay. Are there any other questions? All these equations are from the standard textbooks only, so no need to worry. We can easily write these equations once you know the equation. Else, sir?
Participants have any further questions? Only those two questions are there, ma'am, in the chat box.
Okay, okay, sir.
Ramkrishna.
She said, okay.
Try to log in
All the
using my
sessions are
system.
completed. Move on to validate the system. Selection, madam, from some other area.
Sir, I'm trying to log in using my laptop. So you can go ahead with your validatory functions.
Okay, thanks. Sir, Ramkrishna sir, voice breakout, sir.
Selection.
Yes, sir.
Rishi said,
Yes, sir.
hello, Rishi sir, am I able?
Winpardun, sir.
New messages.
Hello, sir. Ma'am, shall I stop the sharing, ma'am?
Yes, sir, you can stop. I'm trying to logging in using laptop so that I can switch on my video.
Okay. Rishi.
Sir.
Hello.
Sir, Winpardun, sir.
Yes, sir, you are audible.
Breakout. Hello, sir.
Rishi sir.
Yes, sir. Yes, sir.
Okay. Shall we proceed to the validity?
Yes, sir. Sure, sir.
Okay. Thank you, participants. This validity session, this takes only 5 to 10 minutes only. And after this validity session, the link for the test will be activated, and you can take the test. And you can submit the test up to 5:30. Okay, Rishi?
6 we will keep, sir.
6 p.m. You can submit the test up to 6 p.m. And submitting the feedback and submitting, taking the examination is mandatory, and you will be given certificates by the ISTE itself. Anyway, my dear friends and participants across India, a warm welcome to you all for this validity of the AICTE-ISTE sponsored 1-week online induction program on millimeter wave frequencies. My special thanks to the principal of this college, Professor G.S. Prasad, for giving us this opportunity to conduct this program. I sincerely appreciate the enthusiasm of the participants in the field of RF communications, millimeter waves, and terahertz communications. We have received more than 200 registrations from all corners of the country, particularly from teaching faculty and research scholars. However, we could able to accommodate 100 participants only as per the guidelines of the sponsoring authorities. Resource persons from IITs, NITs, IIIT, and other reputed institutions have delivered 11 technical talks on millimeter wave technologies and other RF communication topics. One session is arranged on stress management by Swami Bodhamayananda, Director, VAHE Hyderabad. And in fact, the stress management session is a mandatory as per the guidelines of AICTE and ISTE. My sincere thanks to ISTE for sponsoring this event at our college under AICTE, ISTE Pressure Induction Program scheme.
Sir,
I
video
appeal to all participants.
video on change. Participants.
I once again convey my best wishes to all the participants. My sincere thanks to ISTE for sponsoring this event at our college under AICTE ISTE Refresher Scheme. I appeal to all participants, those who are not members of ISTE, please get a membership as soon as possible and get benefit out of it. I once again convey my best wishes to all the participants in this induction program, and I wish that you transfer the knowledge gained to these lectures delivered in this induction program by eminent researchers in the millimeter frequencies. I would remember one famous quote, that is, man with an experience is never at the mercy of a man with another. I have no doubt that this experience will be useful in finding new research problems in the field of terahertz communications. I conclude my remarks with a famous quote, what I hear I forget, what I see I may remember, but what I do I understand. It is said by Confucius in the year 451 BC, a very old quote, but has got a sanctity even today. Thank you one and all, and I request you all participants to attend phase 3 induction program that will be conducted in the May 2020. I request you all participate in phase 3 program also. And I would like to know the feedback from the participants. Any of the participants, you can share your feedback. It is said by Confucius in the event today. Thank you one and all. It's to attend phase 3 induction program, that is about this program for all these 6 days. 2020. Somebody can share your feedback. 6 days. Can you share your valuable feedback to us?
Yeah, good evening to all the participants. Good evening to all the participants.
Meanwhile, can you please switch on your camera?
Yeah, good evening to all the participants. I'm Venu Madhav, working as assistant professor from Department of EC, PVPSCT. Here today in this momentous event, I would like to remind you that do not think that our learning will stop here. Okay, let us treat this event as a gateway to high level of learning and a new task in our hand to better understand and knowledge infused in this session. Let us handcraft this and master it and use it for the benefit of continuous research. This workshop is also planned in such a manner that to make us realize that in our real life hardship and in our job, family and social life can be balanced and how it can be achieved through the people that are organized in a very beautiful manner. I am thankful to the resource persons Dr. N.S. Namagaru, Dr. Numal Kanti Garu, Dr. L. Anjaneyulu Garu for creating a keen interest in the areas of millimeter wave technology, and Dr. D.T.P. Madhav Garu for introducing antenna maker software and how to publish a research paper and use resources for publication, along with a hands-on session on the antenna modeling concepts using antenna riggers. And I am very grateful to the knowledge delivered for the application-based antenna modeling by Dr. Y. Ushadevi Garu, Silekhana Garu, and Dr. Prabhakar Garu, who have given their valuable knowledge and sharing the knowledge and their time. I hereby appreciate and congratulate the convener of this meeting, Dr. Y. Ramakrishna Garu and his team, college management, for their efforts, and not only for arranging the sessions but also on a continuous and rigorous follow for delivering to the updated content, and which is very much helpful for the development of the faculty on for their own purpose and the benefit of the students. And I can say the overall event has been a successful one with the knowledge that has been delivered from the FDP one that I have been received, and similarly knowledge that I have received from the FDP two. I want to extend the same sort of a knowledge as well as gain some more significance in the FDP 3 also. I'm very much keen to know whether the FDP dates will be scheduled in line with the continuous subsequent months. Thank you all for your efforts during the entire session. I have seen that every participant has reached equal to do hands-on experience, gain knowledge, and try to develop some sort of a cordiality between all the participants. Thank you, one and all.
For the participant.
Okay, sir. Thanks for organizing such a wonderful event.
Thank you very much.
Hello.
Thank you.
Hello.
Hello.
Amarnath Sharma, sir, you can talk.
Sir. Very good evening, sir. Hello, sir. Very good evening, sir.
Good evening,
Sir,
Amarnath,
if I'm not disturbing you, I just want to say special thanks to Dr. Y. Ramakrishna sir and Ruchendra Babu sir for giving me such a wonderful opportunity delivering the sessions in this FDP program. Thank you very much, sir.
Welcome, madam. In fact, it is
Okay,
our
sir.
pleasure.
Thank you so much, ma'am.
Hello. Good morning to all.
Yes, sir. Amarnath Sharma, sir. You can
Sir.
proceed.
Good morning to all. Myself, Amarnath Sharma, research scholar in KL University in the area of RF engineering and antennas, and currently working as assistant professor in SR8 Engineering College, Anantapur. I'm very happy to share my views regarding to this workshop because it is the second phase. There is a good improvement, good knowledge when compared with the first phase. In this particular second phase, most of the area, that is very good areas are covered during all sessions. Especially the phase 2 session is very much elevated, very greatly elevated by Mr. Sharma sir and Kanti sir. And they started the program very greatly, and the rest of the people did very good job. Especially Mr. Madhav sir has given a good idea regarding the publications, and I think a new software has been introduced by Madhav sir to us. I wish all the people can work on that software also. And of course, the entire session is based on HFSS. That is very much useful because most of the people are working on HFSS. So the workshop is probably went smoothly to all the participants who are really watching these videos. And special thanks to the organizing team because they are providing the YouTube links, because now the people are busy with their college works. And so we have time to watch these videos in the evening, and we are following the videos very regularly. But the problem is we miss the queries section. The participants who are having, we are not supposed to work online during the session. They lost the query part. Probably they might have some doubts, but they are not clarified. That is the only drawback. But a part of that, the organizing of the program is very well, and especially Mr. Sharma sir. And the second day, on 17th, we have gone through the reconfigurable antennas, and the same reconfigurable antenna concept again by Mr. Ma'am on the next day. So the arrangement is very smooth and very neat, and thanks for the good level engineering college for providing such a beautiful workshops, and thanks to the management of the good level engineering college, and especially to the department of ECE for providing such a good workshops in the area, in the field of antennas especially. And the topics which covered are really good, and they are useful for the research scholars who are really wanted to work on the software, that is the antennas, especially if the people are thinking this is a radiating field, so we have to be a part of this area. But with these workshops you are making all the radiation to the world, very good radiation to the world, sir. Thank you very much to all the organizing committee, and Mr. Ramkrishna sir also. Ramkrishna sir, thank you for providing this phase 2, and I wish the phase 3 also should cover much more topics, much more advanced topics beyond this particular phase 2, and I wish you people need to conduct more programs like this. Thank you, sir. Thank you so much, sir.
Thank you, sir. Any other participants?
Thank you, sir.
If any of you would like to share your feedback, please, it is very valuable to us. We can improve in different areas, and we can provide more useful knowledge into our face. I request all of you, if you have anything to say with us, please.